go back to something we talked about a few weeks ago. I actually shared this document with you back some time ago. This is when we talked about Boolean expressions and Boolean algebra. These are a list of rules and a couple theorems. We talked about De Morgan's theorems and some laws that you use with Boolean algebra. So remember that Boolean algebra is the algebra of binary systems. And some of these, probably most of these, if you look at them and think about them, they actually make sense. For example, like number one, right here it says you have A or zero. Remember the crossbar represents OR logic, and what you would think of as multiplication, the dot or X represents AND logic. And so like the first rule says that if you A OR with the zero, you're going to get whatever value A is. So if this A is a zero, you have zero or zero, which would make the A a zero. Or if A is a one, you OR a one with a zero, then you get the same thing back that you're ORing it with. So if you OR something with a zero, you get whatever you're ORing it with, you get that same binary quantity back. So if you think about that, that one makes sense. And you can go through like each one of these, and they pretty much make sense. You know, so I think over here you get to some of the laws. You might have to think about these a little bit, but the point is that if you put any one of these in the truth table, you will see that the left and right sides are logically equivalent. Or if you evaluate these using Boolean math, you'll see that the left and right side are equal to each other. And the reason we use these in digital is we use these to take complex digital circuits and reduce them to less complex digital circuits. Now, what you're doing with the digital circuit is you're representing not a digital circuit, but logic. You're using the and or not logic to represent or to implement a PLC program. So we can use these rules right here. If you have a program or portions of a program, you can actually use these rules to simplify the program. And if you guys were in another major, say if you're in electrical engineering or electrical engineering technology, then you'll be expected to learn all these rules and to be able to apply them to a Boolean expression to minimize the logic. But fortunately, there's a better way, because if you use Boolean algebra to minimize logic, if you use Boolean algebra to do that, then your ability to minimize the circuit or the program is going to depend on how familiar you are with these rules and how well you use them. And so it would be nice if we have a way to minimize logic expressions that don't rely on these rules. And that's what I want to talk about today. I want to talk about something called K-mapping. A K-map is a technique that we use, kind of a structure and a technique we use to minimize logic circuits or parts of your PLC program, and we don't have to rely on these rules. But I do want you to practice using these rules just so you can see what you don't have to do. So we've already talked about De Morgan's theorem, and we've used these theorems before. But on homework 6, I know some of you sent me a couple texts about homework 6. I published it a little bit too early. I think it might have became due, but I reactivated it, and it's not due until 1 week from today. But in homework 6, what you want to do is study those rules on the previous page I just showed you. And then what I want you to do is to try to apply those rules to this expression and minimize it. So it kind of reminds me, if you guys remember back in math when you did the trigonometric identities and you had to basically minimize a trigonometric equation. It's kind of like that. You're going to apply those rules to expressions here, to the terms, and see if you can get it down to the simplest expression that you can get by applying those rules and those laws. So just kind of play around with that and see what you can come up with. And at the bottom of homework 6, I've actually done this problem in class in one of the videos when we talked about truth tables. So basically what they want you to do is to take one of De Morgan's laws. That's the one where we say break the line, change the sign. Take one of De Morgan's laws, either one, put it in the truth table, and prove that the left side and the right side are logically equivalent to each other. Now, I don't remember which video we did that in. You guys might recall it, but I actually did this truth table. I did one of the Morgan's laws, or I did an example of this. So maybe if you don't see at first how to do it, search for that video. And if there's any confusion on what to do with there, you can ask me. We'll meet again on Wednesday and on Friday. You can ask me about it. Now, maybe I'll do another example of that. But for right now, I want to get into the K mapping and talk about that. And at the end, if there's some time, there was a couple of problems. Well, one problem was on the homework 3. People missed that. Now, homework 3, you got a grade for it. And pretty much if you did homework 3, you got 100%. Honestly, I just graded it for completion. Most people got most of the problems right, but there were some people that missed problem number 3. So I want to just talk about that, because you got 100. I don't want you to think if you missed problem number 3 and I gave you 100, I want you to be aware that you might have made a mistake. So I want to talk about problem number 3. And then in the labs, forget which lab it is. There was a couple, I think it was lab 2, where you had to take logic circuits and convert it to the actual gate circuits and convert it to a PLC program. There's a couple of those problems I want to just, people tend to miss 2 problems in that list. I want to talk about those if there's time left, but we'll see how it goes. So let's talk about a K-map, and let me go to the camera. So this K-map is short for Karnaugh map, and a Karnaugh map is, as I said, a technique, or you can think of it as like a structure. It reminds you of a kind of cells from like an Excel spreadsheet. It's these cells that you group together a certain way, and you can actually use these cells, if you number them the right way, to minimize logic expressions and not have to use those rules that we talked about. So what I want to do today, guys, I'm not going to answer any why questions. So we're not looking at, well, I don't want to talk about the theory of K-maps, why they do work. What I want you to do is to learn how to use it, and we can worry about the whys and the hows later. So how do you use a K-map is what I want to focus on. So let me just show you. A K-map is basically just a group of cells, and it's always going to be a power of 2. So you can have 1 cell, you can have 4 cells together, 8, 16, 32. It's always going to be a power of 2. And I like to start with 8 cells. So I'm just going to show you this table. It's like a table. And 8 cells. So this is a K-map. And a couple things you got to realize about this group of cells. So we call this a 2x4 K-map. A 2x4. 2 columns, 4 rows, 2x4 K-map. And they expand from there. We want to start with this one. So a couple things. The first thing you want to know how to do is to number the rows and the columns. And what we do is we number them in binary, but we count. We're going to count like this. Remember, in binary, we start counting with 0. So you can count 0, 1, 2, 3, right? But the count's going to actually be like this. This will be 0, 1, 2 down here, and we'll come back up for 3. So we'll go 0, 1, 2, 3. But we're going to do it in binary. So like this row right here is in binary, it'll be 0, 0, 0, 1, 1, 0, 1, 1. So the count is 0, 1, 2 at the bottom, and then 3. So the first thing you got to be able to do to use this K-map correctly is get the numbering sequence correct. You got to number it this way. So my rows are numbered this way, and then my columns are numbered like this. So this is column 0, and that's column 1. So I sent out a announcement on your Canvas and asked you to print these papers out. The worksheets we're going to use today, we're only going to use one of them today. If you didn't print it out, it's okay. You can just copy it down on a piece of paper. But you do want to have pencil and paper handy for what we're going to do today. And it will help if you have coloring pencils. I should have put that in the announcement. You don't have to have them, but it'll help a lot if you have coloring pencils or pens. So if you have that handy, grab a piece of paper, grab some coloring pens or pencils, and if you don't have coloring pens or pencils, you can still make it work. So, well, why do we number it this way? Well, what we do is, in this corner, I'm going to write the variable A, B, C, and the reason we number it this way is because basically this A right here, the column, this first column is the value of A can take. So A here can be a 0, 0, 1, 1. B can be a 0, 1, 1, 0. And this is the value for C. C can be a 0 or a 1. So if you think about it that way, then each cell, and this is important what I'm about to say, each cell has a binary value. And all you got to do is start over here on the left and write the A and B value first and then the C value. So for instance, the value of this would be 0, 0, 0. This is A, this is B, and this C. This would be 0, 0, 1. This will be 0, 1, 0. This is 0, 1, 1. This is 1, 1, 0. This is 1, 1, 1. This is 1, 0, 0. And this one is 1, 0, 1. So each cell has a binary value. If you look at this, what's important is that you notice that if you go from one cell to another, each bit changes by just 1. So for example, let's say if I go from here to here, then this bit flips from a 0 to a 1. Or if I go from here to here, this bit changes from a 0 to a 1. Or from here to here, you can see each bit changes just by one binary digit. And that's important because what we're going to do is if a bit changes as we go from one cell to another, if a bit changes state, if it flips from a 1 to a 0 or vice versa, then what we can do is that we can eliminate that variable. And I'll give you an example of that in just a second. But the first thing I want you to make sure you understand is how to number the rows, how to number the columns. And once you have the correct numbering of the rows and columns, you should be able to get the binary value of each cell. That's important because later on, in a couple days, this actually relates to truth tables. So what happens is we can map Cardinal map, K-map. It maps directly to a truth table. And if you get this screwed up, then your truth table is going to be screwed up. So you got to get the numbering right. 0, 1, binary 2 at the bottom, come up with 3, and then 0, 1, and then be able to put the binary value of each cell in the cell. So I think that's pretty straightforward, pretty easy to do. The next thing to talk about with a K-map is something called an adjacency. So what I did, and I don't know if this will show up in the camera or not, but I made like a K-map, but I numbered the cells with decimal numbers. So I got cell 1, 2, 3, 4, and so forth. So if you guys can see that, an adjacency or adjacent cell are cells that are directly next to each other. So like, if I hold up the paper, 1 and 5 are adjacent, 1 and 2 are adjacent, 5 and 6 are adjacent, but 1 and 6 are not adjacent. So adjacencies like don't work across a diagonal. So this cell and this cell, they're adjacent. This cell and this cell are adjacent. But if it's a diagonal, these cells are not adjacent. So diagonals are not adjacent. But there's something else. There's something called wraparound. Like I can take this K-map and I can actually fold it around like this so that the top and the bottom touch each other. If I do that, if I roll it around like this, so the top and bottom of the K-map touches, then you can see that cell 1 will touch 4, and cell 5 will touch 8. So this cell and this cell are actually adjacent, and this cell and this cell are actually adjacent. And when you do it that way, it's called wraparound. So I can actually wrap this around like that, and I got an adjacency between this one and this one, and this one and this one. Even though they aren't physically next to each other, they are. If you wrap them around, they actually touch each other. So that's half the battle. If you understand and you see, well, if you see clearly how to number the rows and the columns, and you understand what an adjacency is, then the rest is just pretty simple, because what we're going to do is just kind of like we're playing a game. What I'm going to do is I'm going to put something in these cells. I usually use like a check mark. Some people put I don't like to put a binary number in there, because then people get confused with the ones and zeros here. So I like to use like a check mark. So I might put a check mark here like that. So I put a check mark, maybe 2 check marks. So what happens is I'll give you a K-map, and it'll have a member. I call these a member. There's 2 members up there now. It'll have a check or a member, a group of members. And what you want to do is you want to group the members together. When I say group them together, I mean you want to just put it like a circle around them like that. So that's one group. Now there's a rule. There's rules to how you can group members together. Well, I should say there's a rules to the number of groups you can have, the number in the group. You can have a group of 1. You can have a group of 2. You can have a group of 4. You can have a group of 8. It's got to be a power of 2. So if I put a check right here, that can be actually not there. So if I put a check right there, and this right here, that's a group of 1, that's a group of 2. Now let's say I had this. Let's say I had this. You can't have 3. You can't have 3, but you can have 2 groups of 2. You see this one? Even though I've already used it in one group, I can actually do that. I can reuse a member. The fact that I circled it once doesn't matter. I can reuse a member. So the object is you want to circle these members, and you want to have a group of 1, 2, 4, or 8. You want to circle the largest number of members you can that follow this scheme right here. So the largest number, and then you'll have the fewest number of groups if you have the largest number of members in each group. Now, why do I want to do this? Well, what happens is, like right here, you write A, B, C, and then this is a group of 1. So pretty much the algebraic way of writing the term for this cell, each cell has a term. The actual way of writing the term is like this, A, B, C. And what I do is I come over here and I look to see if I have a 0. If I have a 0, then I'm going to knot the variable. If I don't have a 0, it's unknotted. So like right here, I got A, B, C, and I see A is a 1, B is a 1, C is a 1. So I leave these alone. But if I had put that check right here, or let's just look at this one. If I look at that one, then for this cell, I have A, B, C. A is a 0, so if it's a 0, I'm going to knot it. B is a 1, so I'll leave it unknotted. But C is a 0, so I'm going to knot it. So not only does every cell have a binary value, every cell actually has an algebraic value. I can write it in terms of A, B, and C. So like this one, I have A, B, C. Well, A is a 1, so I leave it unknotted. B is a 0, so I knot it. C is a 0, so I knot. You might say, well, what the heck are we doing? I see what we're doing, but what are we going to do with it? I mean, how does this help us? Well, this one really doesn't do much for us. If you have a group of 1, when you write the term for it, you get whatever the term is. But you see right here where we have a group of 2 that we circled in red. What you can do is this. You write out the term A, B, C, and then for this red group, as I move from left to right through these 2 cells, you're looking to see which bit changes state from a 0 to a 1 or a 1 to a 0. And anytime you move this way, A and B are going to remain zeros, right? In this cell, the value of A is 0, the value of B is 0, and in this cell, the value of A is 0, the value of B is 0. The only bit that changes is C. In this cell, C is a 0, and in this cell, C is a 1. Anytime a bit flips, goes from one state to another, you eliminate it. So C is out of there. I can do the same thing here for the green. All right, A, B, C. And this time I'm moving vertically. So I see that since I'm moving up and down, C is never going to change. It's always a 0. So I'm going to nod it. Looks like B is going to change. B changes from a 1 to a 0. So I get rid of the B. And I see that A is a 0. So if it's a 0, I got to represent it like that. So you can use this grouping, these groupings, to get terms that eliminate variables. And then you put the whole thing together into an expression. Then I might call this X equals AB. You OR them together. And then that would be my final minimized expression. So that's kind of what we want to practice. Now, I'm showing you the tool before I'm showing you how to use the tool. So I know you're sitting there wondering, what the heck, what's this going to get? Just trust me. Learn how to do this, and then we'll apply it in the next couple of days, and this will make perfect sense. The other thing you want to just remind yourself of how to go from this expression to gates. So if I want to write this as gates, I got AND gates ORed together. So I got this first AND, it's AB. The second one is AC, but that's not it. So I got to put bubbles over here. Inverters. And then I got a 3-input AND, ABC, and they're all ORed together. So you should be able to do that. And then you should be able to take this, and you have practice doing this when your simulation, in your lab book, but then you should be able to take this and represent it as ladder logic. So I think everybody, I looked at the labs, and pretty much everybody did okay with doing that, with the exception of 1 or 2 problems that if we have time, I'll go over those problems in just a few minutes before we end. So that's the game. So it's hard for me to explain. It's easier for me to just show you. I think when we do an example, you'll kind of see how to do it. And so what I did, I made up these sheets for you to practice with. So what I want you to do now is take out a sheet of paper, or if you have this printed out, you can use this. And I want to do that first one together, A, K-map A. So if you're using paper, just take out a sheet of paper, draw this K-map, number the K-map, rows and columns, and then I want you to circle the groups that you think are here on this K-map, K-map A. So I'll give you a minute to do that. And while you're doing that, I'm going to draw it on the board. All right, so on the handout, there are ones there. I think at the time I created the handout, I probably didn't know how to find the check mark, but I recommend not making the binary numbers the members. Put a check in the box. It's easier. It just looks simpler if you put X's or some other way of indicating a member. So I use check marks. So the first step here would be to number your rows and columns. So let's do that. And then after you number them correctly, you want to write out your variables. So if I have a 2x4 K-map, I can use that to represent three variables, A, B, and C. So remember, what's below the A are the values that A can take, what's below the B are the values that B can take, and C can take 0 or 1, depending on the cell we're in. So after this, what you want to do is you want to group them. So you want to circle the largest number of members, but you can only circle 1, 2, 4, or 8 of them. You can't circle 3. You can't circle 6. It's got to be a power of 2. But you want the largest number of members in the group because you want the idea is to have the fewest number of groups. You want the fewest number of groups. So go ahead and group these and see what you come up with, and then we'll do it together. And it should be pretty easy to see that you got two groups of 2s here, right? So I got a group here. And I got a group here. And you might think to yourself, well, what about wraparound? Can I do this? Can I have one here and one there? And the answer is you could, but remember, part of the objective is to have as few groups as possible. So if you did that, there's no reason to do that because every member is already included in the group, and we don't want 3 groups. We want as few groups as possible. Here we got 2 groups. So we got 2 groups of 2s. So once you do that, we just see which variable is eliminated. So I like to write them down at first, keep track of them. So obviously I'm moving this way. So I move back and forth. A and B never change value. The only variable that flips is C. C flips from a 1 to a 0 or 0 to a 1. So I get rid of it. And I go back to check to see if I have zeros. I do. Both A and B are zeros. That means for this term, I got to knot them to represent the zeros. And then for this one, this time I'm moving up and down. So C is going to stay a 0. So I can just go ahead and knot that right away. And the bit that changes looks like B changes. B changes from a 0 to a 1. So B is eliminated. And A is a 1, so I don't have to knot it. So my minimized expression would be X or Y. I got A, B, not, or A, C. And then after this, you should be able to write this as a gate or PLC program or a ladder logic. So that's the game. What I want to do is I gave you a few of these on the practice sheet. And I think by the end of the practice sheet, if there's any confusion, by the time we get to the last one, I think everybody will pretty much understand how to do this. So any questions on what I did before I give you the next problem? Any questions or comments? Somebody's mic is open. Let me see if I can figure out. Okay. Okay, let me go back to the sheet, and I want you guys to try the next problem, and then we'll talk about it in a few minutes. So B, K-map B, see what you can do with it. So how many groups do we have? Anybody?
You have two.
We got two. Okay, which two do you think we have?
The it's kind of hard to explain.
Anybody get a different answer for the number of groups?
3.
Three. Okay. Which three?
You got the single group up in the
Yep.
upper right corner,
Yep. This is a group. He's correct. This is a group of one.
and then you've got the vertical 2 and then the horizontal 2.
Right. Because remember, we can share that. So I got this one. So you can't have a group of three. So you can't have two because you can't have a group of three. But you can have two groups of twos, and we can share that one. So whoever said three, you're exactly right. So you got this one.
When you're talking about the fold over,
The
Can you-
wraparound.
yeah, the
Yep.
wraparound.
Yep.
How does that like? Couldn't you do that with this one or no?
Which one wraps around? I mean, if I had another one here,
Right. Oh, that's let to be touching. Okay, I see.
yeah. Say that wasn't there, and I had one here, then these two would be it. We'll
Oh,
get to one like that.
I got you. Okay.
Yeah. Okay. So let's get the term for this. So obviously we're going this way. So C's out of there. I don't have any zeros, so that's good on that one. And then this is, of course, there's nothing you can do with that one. But this one, C's gonna stay a 0, so I gotta knot it. Looks like A changes from a 0 to a 1, so A is omitted. So my final expression is X or Y equals, it doesn't matter the order you write these in, of course. And then you guys should be able to write the logic circuit from this and the ladder logic for the PLC.
Shouldn't
what?
the A, B, C, the A, B should be knotted?
Yep. Thank you. This should be knotted. He's right.
Well, the C wouldn't be knotted, right? Because it's a 1.
Not, yeah. Yeah, so A and B are zeros, so I'm getting ahead of myself. These are knotted, and this is not knotted, so thank you. All right, so that's it. So, I mean, now it's just practicing. I think you'll see again by the end of this, you'll see how to do this, and then what we'll do is we'll go to bigger and bigger K-maps. In theory, you can have multi-dimensional K-maps, but they get kind of complicated. After you can go up like another variable. You have a 4x4, and then once you go above 4 variables, then they're three-dimensional. They look like the Rubik's Cube thing. They look like that. I'll show you one if you want to see it, or at least show you what it looks like. But when you go to multi-variables, then we'll have computers do this for us. But I want you to see what the computer is doing. So this is kind of what it's doing. Let's try the next K-map, C. Oh, I forgot to, damn it. Let me turn this off. I forgot to flip that off because even though you guys can click off on that when I make the recording, it's the document is in the way of the video. So let me show the final answer. So people going back looking at the video can see if they got the right answer. And then I got to remember to take that document down when I'm going over the problem. So what we got is this. And we're going to move on to the next problem. So move on to the next problem, and then I'll remember to take the document down so we can record how we get the solution. So see what you can do with K-map C. All right, how many groups on this one?
Is it 3 groups again?
Yep. Got a group right here. We're moving that way, so C is out of there. I don't have any zeros, so I'll leave these unknotted. You got a group that you can share that one. C is going to stay at 1. A changes state, so A is out of there. And then you got the group of 1 by itself, this one. And so that is the expressions for that. Of course, you put them together into an equation. So that one wasn't too bad. Now the next ones are kind of interesting. So let's look at that next one to see what you do with, oops, that's the wrong one. See what you can do with D. See what you can do with D.
For that ABC at the top, would that be knotted?
Oh, I don't know why I keep doing that. Thank you. I'm sorry, guys. I don't know if I'm trying to do this fast. I don't know why I know why I'm doing this fast. I'm on like the second day of a fast and I haven't eaten. I think my mind is foggy or something. I don't know why I keep doing that, leaving those unknotted. But yes, thank you again, whoever corrected me. And I won't make that mistake again. All right, so we're doing D. How many groups are on this one?
Four.
Okay, you think there's 4?
Is it 3?
4. Somebody said 3. The person that said 4, which ones do you think are grouped together?
You got the top 2 that are horizontal,
Okay.
and then the bottom 2 are horizontal, and then you've got the shared vertical 2.
Yeah. Okay. Now somebody said 3. Why you say there's 3?
Can you do like a wraparound with the top
Exactly.
horizontal and the bottom horizontal?
Right. So remember that you'll get fooled by that. Even though these seem like separate rows, I can actually wrap these around into a whole group. And I want to circle the biggest number of members. So I actually can group these 2 with these 2 by wraparound. I can wrap those around. And so I got A, B, C. C is gone, right? Because when I move this way in this grouping, C changes. So I got to check the state of A and B at each side of these. You got to be careful when you do wraparound and just kind of record your bit value. But you can clearly see that A is a 0 here in this cell, this row, but down here it's a 1. So A is the one that flips. So A is out of there. B is a 0, so I knot it. Anytime you have a group of 4, you'll end up with just one single variable left. So Yeah, so you do that wraparound, and then whoever mentioned the group of four, you are correct in that you can share these two. You can share those two, but just don't forget about the wraparound. So this, we'll keep C, and we'll get rid of B, and then this one. Again, we'll keep C, but C is a 0, so I gotta nod it. And this time I'm gonna get rid of B. And A has a value of 0, so we gotta nod it. So that would be the term for each one of those groups. So that one kind of threw wraparound at you. So you can see, think about that. And you gotta do the same thing in the next problem. So any questions over this one? Everybody see what we did?
Could you also do 2 groups of single boxes or checks?
No, because you want the largest number, in order to be guaranteed to get the minimum number of terms, you want the largest number of members in each group. That's a 2, a 1, 2, 4, or 8. So you want as few groups as possible.
Wouldn't it be the same amount of groups? Like if you did the wraparound and then had 2 singles, wouldn't it still be 3?
I think so, but I think you want to minimize. Like it'd be easier if you like are minimizing variables. So if you just circled the single checks, then you wouldn't be you wouldn't be erasing any variables, right?
So so
Okay.
if I hear you, yeah, so you're saying just circle this by itself? Remember, you want the largest number of members in the group. So you can circle this by itself, but as I think as your colleague said, you want the largest number of members in a group to guarantee that one of them drops out. If you have a group of 1, you don't lose anything. So yeah, that's a good question. Anybody else have a question?
Yeah, when you simplify, is that just simplifying like the end result equation of x? Like, would you still end up with the same? Are they logically equivalent no matter how you do it?
Yeah. See, we're actually working backwards. That's why I say don't worry about what we're gonna do with this. Just learn how to play the game. So this is actually, we're kind of working backwards from an answer. So yeah, this isn't gonna make sense till we apply it to something. But basically what you're going to do is given, let's say, an expression or a program, you'll convert it over to Boolean, an expression. You convert it over from English to Boolean. And then you'll have to write it a certain way because you can't put any old expression into a K-map. It has to be represented a certain way, and I'll show you that in the next class. Well, on Friday, because I think in the next class, we'll move to a bigger K-map. But once you get the equation written the correct way, then you'll use the K-map to minimize it, and then we can take the K-map and put it in the truth table, and we can do other things with it. You can actually use the truth table to help design a program or circuit, or you can go from the truth table to the K-map or vice versa, depending on what you're doing. So yeah, this is kind of the end result. So it'll make more sense on Friday. Just kind of just roll with me, and then you'll see when we apply this. Let's go ahead and do D, because D is very interesting. I want to see how many people get this one correct. And then if you have questions, I'll take any questions after that. See if you can do with E. I said D, I meant E. Okay, how many groups here? Anybody want to take a shot at it?
3.
Okay. Sam said 3, and somebody else came in on the mic and said 3. I think there are 3 groups. Now, which 3?
You got the upper 4, the first 2 rows.
Okay, so we got this group right here, the upper 4. Let's go ahead and, while we're doing it, just so it's a little easier. So since I'm moving this way, C's got to go. And since I'm moving this way, it looks like B changes from 1 to 0, so that's out of there. And I see that A is a 0, so I got a 9. Okay, so that's one group. What's the other group?
4 in a row in that first column.
All right, so I got 4 right here. That's an easy one to do, because the only thing that's going to stay constant is C. So A and B are gone, and C is a 0, so I got a 9. And where's the third group?
Just the bottom 2.
Is that correct? Is it just this group here? Because I got to
The
include
bottom 2 and the top 2.
Exactly. Yeah, I got to include this. So at first thought, most people say, well, I can share these. But remember, you want the group to be as large as possible, because the bigger the group, the more variables we get rid of. So even though you can circle that one, you really want to use wraparound. Even though we're only looking for that one, you still can share all these other ones, even though they've already been used. And that way, we'll get rid of 2 variables. If we make the group bigger, we'll get rid of 2 variables instead of just 1. So if I move this way, let me do. So as I move this way, C is out of there. So I got to check A and B in this cell and this cell. The one that changes is A. So B is still there, but B is a 0, so I got to knot it. So this is interesting. This is A naught or B naught or C naught is a minimized expression. Now, like I said, I'm only telling you like half the story, so I know what the heck are we doing? You'll see. What I want to do on Wednesday is just give you a bigger K-map to practice with, and on Friday you'll see how we use this stuff. Any questions over this? And I do want to. There's a couple things I want to talk about. There's some people that missed some problems on homework 3, one problem on homework 3, and then a couple of labs. I just want to go over it because I don't know any other way to. It's hard for me to grade on Canvas because I can't really, I can say that you missed this problem, but it's hard for me to give you the solution. And I don't want to publish answer keys because I use all this material over and over again, as I'm sure some of you already figured out. So any questions over this before we leave this? If you go on YouTube, and I know some of you'll go and review this on like YouTube, sometimes instead of using, they'll just put the A's and the B's right here. They'll call this A naught, B naught, A naught, B, and so forth. Kind of a different way, but ultimately it's the same thing. You get the terms, you can see the terms a little more clearly. I like to use these values only because the next step is we're going to show you how the K-map relates to a truth table, and you can't, it's easier to see if you just look at the binary values, in my opinion. But you'll see other people do it different ways depending on whose website or whose book you pick up. So any questions over what we did or any of the other problems? Or okay, well, let me, there's a couple people, we just got a couple minutes here. Most people on homework 3, that was the one where you're doing the binary arithmetic, and I think for the most part, pretty much everybody did okay. There was one problem though where you had to do the subtraction, and that was 2's complement subtraction. And problem number 3 told you that referred back to problem number 2. 2D specifically was this problem that you have a 1, 1, 1, 0 minus 1, 1, and that's base 2. And they asked you to do 2's complement subtraction. Some of you didn't get the right answer. You got to remember that these numbers, even though I wrote it on purpose this way, but if I have a 4-bit number here, you got to have a 4-bit number over here. So you cannot write it like this. You cannot say I got 1, 1, 1, 0, and I'm subtracting from it 1, 1, and use 2's complement subtraction. You got to put the leading zeros there. So when you take the 2's complement of that, you actually have numbers out there. So if you didn't get the right answer and you're wondering why, what I saw is probably, I don't know, maybe 5 or 6 people didn't do that, so you weren't able to get the right answer. So the number of bits have to match, and that always happens in the computer because, excuse me, these numbers are actually stored in registers, and you can't have a register, a physical register, and just have like a 1 and a 1 here. There's got to be something in it. It's going to be a 1 or a 0. So the number of places will always match. And again, I did that on purpose because that's a common error that people make when they're doing that type of subtraction. So on your homework 3, if you did it, you got 100. I just graded it for completion. But if you might have done it and gotten this problem wrong, I want you to go back and look at it and make sure. Even though on the final exam, I don't go back to any of this stuff, but it's still good to know the right answer. And then in the lab manual, I forget which lab it was, but there was this one problem where you had to convert gates to ladder logic. So you had this. And what they did, they took they call this M, and they took the output and they fed it back to this OR gate like that. And so over here you had A, B, and then you had C and D in the AND gate directly. So a few people got confused on, well, what do I do with this? And you just act like it's another input. So most people saw that, but you put an M here. And then when you show this as your ladder logic, you just show that as an input. So then I'll have my inputs like that. I don't know if you guys can see the bottom of this, but then you have your, so you just, I think that might have confused a couple people. Most people got it, but there were some people that didn't know what to do with that. So just the fact that, I mean, you can think of it like this if you want, and just call it M. It's the same thing. And then there was another one in that same lab where, oh yeah, this one, a lot of people, probably half the class missed this one. And they were worth 5 points apiece. So if you got a 95 and you're wondering why, you probably missed the one I'm about to show you. So it was this one. You had this. And then they had this hooked to some kind of alarm or something. Yep. So what would the expression be for this? I mean, it's pretty easy to get the expression, right? I mean, right here, this is OR, so I got A or B. But when it hits that bubble, that's knotted. And at this point, I got CD, and they're ANDed together. So over here, if I write this out, I'll end up with A bar B, the whole thing, CD equals X. But the problem is there's no way to implement this in the PLC. You can't, there's no, how are you going to do that? You can't knot an OR. So what some of you realize is, what I can do with that is I can change that I can change that knot. I can move it from the output of the gate to the input if I demorganize. And so this I got you again on like an exam or something. You gotta break the line and change the sign. So if I break the line and change the sign, I end up with this, and that you can put in your PLC. And like I said, maybe half the class got that right. But you got to demorganize that, and then you have A, B, and then C, D. And that was, I think that was it was problem 419 in your lab book. So I just when I see a lot of students missing the same problem, I just want to talk about it. So just make sure it only costs 5 points, so it's not that big of a deal. But just don't forget about the organizing. This is actually what we're going to do the next couple of weeks. You'll get a chance to demorganize again. That's pretty important to be able to do that, because there's no way to knot an output. You gotta, any kind of knotting has to be done on the terms of the input, which means you gotta demorganize. So I'm out of time, guys. I'll stick around if anybody has questions. But I know some of you have things to do after this class. So thank you for hanging in there with me. We'll do more K-mapping on Wednesday, and I think that's it. If you logged on late, make sure you send me a text for your attendance. And then anybody else, if you have questions, I'll stick around after class. I don't have anything going on. So guys, have a great rest of the day, and I'll stick around in case anybody has questions they want to ask about anything.
Yeah, Professor, I have a couple questions about the exam.
Which one? Exam 1?
Yeah.
Yeah, I sent a note out. I haven't done much as far as grading yet. I've been grading your labs, but go ahead and ask me your question. I'll let you know.
I mean, mine got graded. I was just wondering how you got the answers for number 1 and 2. Those ones. Well, 1, I have more of an issue with. Like 2, I understand, but the wording of the question kind of threw me off.
Are you one of the people? Are you one of the people that sent me a text about that?
I haven't sent you a text about it, no.
Oh, okay. I had about maybe four or five people that they had questions about. Do you have it in front of you, the question?
Yeah.
What does it say? I don't even know. Yeah.
So question says, the graph below shows a digital waveform. The horizontal axis is in milliseconds. Calculate the frequency. Write your answer in hertz. And it looks like the wavelength, I think, or the period is like 4 milliseconds.
Okay, I remember that.
So
I can't
to
remember
calculate
micro, but go ahead.
Oh, let's see. It says the horizontal axis is in milliseconds.
Okay, all right.
So I divided 1 by, or like I put 1 over 4 because like 1 over the period equals the frequency, right?
Yeah.
And then I got 0.25, but it says that the answer was 250.
Oh, okay. So it should have been 0.25 kilohertz, right? So you're saying that you did 1 over 4
yeah,
milliseconds, right?
Mm-hmm.
So this would have been, if I divide that, that would have been 0.250. If that was just 1 over 4, it would be let's just say 0.25. But since this is milli,
yeah,
remember that's 10 to the minus third, and when you bring that up, that'll be 10 to the third, which will make it 250.
Okay, cool.
Yeah, and I think I think a couple people had that question, so it wasn't just you. And I don't mean to, I don't know. Maybe I'm not trying to trip anybody up, because I mean, as long as you knew, I'm actually happy if you knew the formula, and I know you had your notes when some of you when you did this, just to do that. So I don't know. I may have to. Let me think about that problem, because it's not my objective to take points away from me for making an error like that. If you knew that the frequency is 1 over the period, which is what I was after. So maybe I'll think about that. I actually texted, or I had a couple texts. I wanted to go back and just kind of think about the problems on the exam, and I may make some adjustments. I just want to see how it reads and all of that. So yeah, I just haven't had a chance to do that yet. Now you said you had another question?
Okay, yeah. So on the second problem, it says determine the bit sequence represented by this waveform. I was able to figure out the bit sequence, but then it says from left to right, write the bit to be transmitted first.
I remember that
and
one.
write it to be transmitted second. So what I remembered from class was always like transferring the rightmost bit first. So I just like flipped the bit sequence around, and that was wrong. So I should have just kept it the right way around. But can you explain like what you meant by from left to right? Like, does the leftmost bit, does that get sent first when it goes into a register or something?
Yeah, so you got to remember this. Let's say this is your waveform. And if you put this on does this red show up when I write that? Can you guys see that? I don't know how well it shows up on the camera.
Yeah, I mean, I can see it.
Okay. So remember, this thing is moving, but it's moving in time, right? So it's just like if I have this a regular Cartesian coordinate system, but this is time and that's say distance or something like that. T0, T1, you know what? This happens earlier in time than that one. So if you think about it like that, is all I was saying is even though, like if I showed you this was a 1 and this was a 1 and a 1, well, people think, well, this thing is actually moving this way and this 1 gets there first. Well, in time, T-I-M-E, this is my axis. So this is the first bit in time. This is the second bit in time. That's the third one. So the actual one to be sent first would be this one, that 1, and then that 1 goes first into the register, and then the 0, and then that 1, and then that 1. So when I said left to right, that's kind of what I meant. But again, let me see how the question's worded and see. I'm not trying to confuse anybody. I'm trying to just make sure you guys understood what we talked about when we went over this. So I'll look at how that's worded. Some people might have asked me about this already, but I just haven't had a chance to go back and think about the problem. And then what I'll do is I'll go back to other classes. I've given this problem before and see how other students interpret it, and I'll make some kind of a decision if I want to make an adjustment or whatever. Grade-wise, guys, don't even, I'm not going to say, I don't think anybody blew exam 1, but the rest of the courses, and I probably shouldn't say this, but it's actually a piece of cake because the next exam, which I'll talk about here in the next couple of days, is a program, and you've already done half of it if you did the labs. So students usually get a or B on that exam too, because it's just a simple program. Well, I don't know how simple it is, but I think it's simple. So that's pretty much, that's done. That's pretty much a given, unless you just don't do it or royally screw it up, which hardly ever happens. And then the third exam is really just a research project, and I don't think I've ever given anything below a 90 on that because it's just you answer some questions and you got 100 points. The only one you got to worry about is the final exam, and all the material we started today and we'll talk about to the end of the semester is material for the final exam, and I think that you'll see that it's not too bad. So no matter what I do with exam 1, I think I've been teaching this course since 1999. And I think in all of those years, there was one student that failed only because he just didn't turn in any work. I remember the student. And there was one C, but every other grade from all the way back in time, since I've been doing the course, has been an A or a B. So, I mean, it's good that we're going through this. And if I may make some adjustments, I may not. I don't know. I'll take a look at it. But grade-wise, I think you're probably pretty cool. I do appreciate you asking questions to understand the material, which is actually my purpose. Grades are important to you guys, but you guys understand the material is what's important to me. So I'll look at these questions. I have a list of them from the people that sent me texts right after the exam. I got a few texts. I'll go back and look at those, and I'll think about them. And it takes me a while because I actually got to go back and look at the way other students answered and all of that in other courses, other semesters, and I'll figure it out. So, is that it? Anybody else? Clay, wait a minute. Let me switch over. Was that ladder that you wrote on? Yeah. For 19? Yeah. I think it was this. Yeah, that was correct. That was the actual answer. Is what I was looking for. Because there's no way. The point of that problem is, you know, when you have that or, actually it was a nor, right? You can't. There's no way to put a nor. There's no way to put that in the PLC. There's no way to implement this in the PLC. So if you had this, the only way to, because you can't have a single bar over inputs. I mean, I can't put a big knot over it like that, right? So you really gotta make this bar go to the inputs and not the output. So the only way to do that is to organize it, break the line, change the sign. And now instead of my bubble being here, my bubbles are here. And that I can put into a PLC because I can knot each individual A and B. So that was the point of that. I think who am I talking to? Clay? Does that make sense, Clay? I had that on PDF and I submitted. Okay, Clay, then I'll check. That's my mistake. I'm actually done now with classes until tonight. I got a night class at 6. But I'll go back to yours and yeah, guys, check your work because I make mistakes. If I mark something wrong that you think is right, send me a text and I'll fix it if it is if I made a mistake. But yeah, you can go ahead and do that, Clay. I'm actually going to do it right now though. As soon as I'm in another classroom, but I'm going to load up the camera and my markers, and when I get back to the office, I will go right so I don't forget. But go ahead and send me a text just in case. As a reminder, and I'll take a look at that and I'll fix it if I marked it wrong and it's correct. And who else do I have out there? I guess it's Matt and Clay. It says 4 people. Thank you, Clay. Appreciate it. Anybody else? Matt, you okay? Okay. Well, guys, have a great rest of the day. See you on Wednesday.